Yeah. Hello, everyone. On behalf of ISI Bangalore students and researchers, I welcome all of you to another talk of Limit Camp 2025. Today, we have with us our speaker, Agniva Roy. He did his BMath and MMath from ISI Bangalore, his PhD from Georgia Tech, postdoc from Louisiana State University, and is now a visiting assistant professor in Boston College. He works in contact and symplectic geometry and applications to smooth low-dimensional topology. He has been the recipient of multiple awards such as AMS Simon's Early Career Mathematicians Award and many more. We are very honored to have him here for his talk titled An Invitation to Symplectic Embedding Problems, Fibonacci Sequences and Infinite Staircases. I'll again remind everyone, please keep your microphone off during the talk. If you have any question, please ask it in the chat. After the talk, you can ask questions. This talk will be recorded and will upload it in our YouTube channel. Please check it out if you need to. Now I'll hand over to the speaker. Thank you, Agniva, for being with us today.
Yeah, thank you for the invitation. Thank you all for joining. I'll try to share my screen. So just give me 1 second. Is this screen visible?
Yeah, it is visible.
Okay. Okay, so I don't see any. So if anyone has any questions in the chat, can one of the moderators let me know? Because I can't see the Google Meet screen. Okay, thank you. Okay, thank you. So hello everyone. Thank you for coming to the talk. So as I said, this is an invitation to symplectic geometry. So I'm very grateful to the organizers for the opportunity to speak. So this talk will be, as in the title, it will be an invitation. So it will not be very technical. The idea is I want to convey some ideas in the research area that I work in. And so I've been working in contact and symplectic topology through my PhD and now. But while I was at ISI, I did not have much idea of what these were. So these words were pretty alien to me when I first saw them. So the hope is that I can convey some idea of why this is interesting and what kind of ideas go into, what kind of tools go into studying these questions. So this is symplectic geometry and topology. It's a branch of topology. And like broadly in topology, there are two kinds of questions people study. So the first are classification problems. So this asks, when are two shapes the same? And if you have ever studied any topology, you might know of shapes as manifolds, which is the more mathematical term for them. But for now, we can just think of them as shapes. So classification problems asks, when are two shapes the same? And now the word same has a lot of nuances depending on what kind of shapes you're looking at, how you're allowed to move one and deform one and so on. And so this is a very rich area of research. So this question started off with the Poincare conjecture about shapes that are homeomorphic to spheres and like that we can detect using some sort of algebraic invariant of theirs. And from moving on from the Poincare conjecture, this has led to a lot of interesting research. The second kind of question is what's called an embedding problem. So the embedding problem asks, when does one shape fit into another? And so this is a slightly different type of question. The tools needed might be different, and there are some more things that may be involved here. And so I'll focus on the second kind of questions today, in not just in general topology, but just in particular to symplectic topology. So as I said, embedding problems ask, when does one shape fit into another? And so before we get into any symplectic geometry, we can look at this example or these kinds of questions just for normal, just for shapes that have no symplectic structure, to say. And so we'll also start using the word manifold for shapes, which is it's a more mathematically rigorous definition of what we think of as a shape. And so here we have two manifolds. It's one of the first questions you encounter when you start studying topology is, if you have a sphere and you have a torus, and so if you think of the sphere as the boundary of the three-dimensional round ball, and the torus is sort of the boundary of the donut, you can ask, well, when does one manifold fit inside another? And so it turns out that we have a complete answer to this question. And we can say that there can be no embedding either way. Now, how do we say something like this is true? Well, the tool we use is algebraic topology. So there's algebraic topology is topology with algebra. Algebra is the study of mathematical structures. It's more the study of numbers, and if you're aware of like groups and rings and so on. So algebraic topology takes a topological shape and associates some algebraic object to it. It can be a number, it can be a group, or it can be something. And this is what's called an invariant. And we can study the invariants to say that, these invariants are not compatible with each other. So there's no embedding of one inside another. And so this might not be a completely satisfactory answer as to why we can't have an embedding of a sphere inside a torus, but it's sort of the punchline that the general theme in topology is you take some manifold and you associate some algebraic structure with it, and you study the algebraic structures to say how much you can say about those shapes and whether they embed inside each other or whether they are the same as each other. So this technique works both for classification problems and embedding problems. Okay. So moving on from that, we can look at something slightly, it'll look slightly simpler. So topology and geometry are two branches. So the last slide was embedding problems in topology, and this is embedding problems in geometry. So geometry is also the study of shapes, but there we impose a little more structure on the shapes. They're a little more rigid. And so in topology that you might have read or you might have already taken courses in topology, or if you have not, you might have an idea that topology is the study of shapes that you can sort of squish and stretch, and the size of the shape doesn't matter so much. It's more an intrinsic way the shape is built that makes embedding and classification problems in topology interesting. In geometry, with that we have something more. We have the size of the shape. The notion of the geometry has to be taken into consideration as well. So in geometry, we can ask the embedding problem of, we have a square on the left, which is the blue square, and we have two rectangles on the right, the green rectangle and the purple rectangle. And we can ask, well, when do any of the shapes on the right fit inside the blue rectangle? And so that's the embedding problem in like the simplest incarnation of the embedding problem for geometric shapes. And so I'll give you all a few seconds to think about it. When does the green rectangle fit inside the blue? Does the purple rectangle fit inside the blue? Okay. So let's look at the answer. And so the answer will be something like this. So I'll say that the green does not fit because the volume or the area of the shape is bigger than the target. So the area of the green rectangle is 5, the area of the blue square is 4. There's no geometric sort of way to fit the 5 area rectangle inside the 4 area rectangle. Now on the purple, I'm telling you that these are some things you can do. Even if you respect the geometry, you can still deform the shape so that the volume is preserved. So you take this purple rectangle, whose area is 3 times 0.8, so it's 2.4, and you can take this 2.4 area rectangle and you can sort of deform it a little bit so that you're then allowed to fold it inside the blue rectangle. So this tells us two kinds of things. So in the topology embedding problem, we saw that an algebraic invariant of the shape told us there could not be any embedding. But here, the algebraic invariant for the green was the volume, which told us we do not have an embedding. But for the purple, we did not have an algebraic obstruction. And then we had to do some clever manipulation of the shape that was compatible with the geometry. And then we were able to fit it inside the blue shape. So that's sort of the theme in a very simple sense of how these embedding problems are approached. You either rely on some algebra to tell you that there cannot be any embedding, or in case the algebra doesn't tell you anything, you rely on some ingenious tricks or constructions to actually find an embedding. Are there any questions at this point?
No questions in the chat.
Okay. All right. So let's move on. So let's look at some types of manifolds that you can consider. And so smooth manifolds are the ones on the top left. Now, the definition of a smooth manifold, if you take a differential geometry course or a differential topology course, is it's sort of involved, but an intuition you can have for it that a smooth manifold is something that has no corners. Okay, you're not allowed corners in smooth manifolds, but there's other kinds of manifolds, and then you can have piecewise linear manifolds. And so I don't know if you're aware of this kind of car that's gone on the market recently, which sort of looks like a piecewise linear manifold. But you can think of a piecewise linear manifold as being some sort of smooth pieces that are fit together along some sharp edges or corners and so on. And then we'll talk about symplectic manifolds. That's what we'll talk about soon. A symplectic manifold is a sort of smooth manifold. So it's a subset of smooth manifolds, but you have this omega that's associated with a symplectic manifold. And this omega sort of gives it some more structure, which is like the geometry. It's like a geometry, but it's something slightly different. But so symplectic manifolds are smooth manifolds with some additional structure. This picture of the symplectic camel will be explained in a few slides later. And then another kind of manifold are complex manifolds. If you've studied complex numbers or complex variables or complex analysis, you're aware of the complex plane. And complex manifolds are manifolds on which you have a structure like the complex plane structure. Like you have a notion of turning left and turning right on that manifold. And just that notion can give a lot of rich structure and really. And so like the study of these 4 kinds of manifolds have overlaps, but they can also sort of go off in 4 different directions. And so we'll focus on the symplectic side of things. But before that, one quick segue into building manifolds. So I'm going to be talking about manifolds that are not necessarily things we can see or visualize very easily. And so one way to do that is to understand how to build a manifold which is higher dimensional from lower dimensional pieces. One way to build a high dimensional manifold from lower dimensional pieces is by taking products. So this is an example, is if you have an interval, then you can say, if you have an interval, then you take the product of two intervals. You can think of that as being a two-dimensional manifold. So an interval is a one-dimensional manifold, and the dimension you can think of as the number of directions you have at every point. So at every point on this manifold, at least in the inside, there are two directions you can move in. So that's why this is a one-dimensional manifold. But if you take the product of these two, you can get a square, which is a two-dimensional manifold. You can keep going. You can take a product of the square with an interval, and that gives you a three-dimensional manifold of the cube. So here we are considering the cube with its inside. And if you think that you're inside the cube, there are three directions you can move. So this gives you a three-dimensional manifold. And then you can keep taking products. So this is a sort of simple way of building high-dimensional manifolds. You keep taking products of the interval with itself, and you can produce these high-dimensional cubes and so on. Something slightly more intricate is a donut. Now, it's not immediately obvious how a donut can be seen as a product, but it turns out that if you take an S1, now an S1 is just a circle. So the boundary of a disk, that's called an S1. It's the one-dimensional sphere. So if you take a circle and you take the product of a circle with itself, the shape you get is actually the same shape as the boundary of the donut. So you can create this slightly complicated two-dimensional shape by starting with the circle and take a product with itself. So this is taking products to build manifolds. And then moving on, the second thing that you can do is called surgery. Now, we won't talk a lot about surgery, but it's something that's used a lot in topology. So I just wanted to make you aware of what this is. And what surgery does, it allows you to take a simple shape and you do some manipulation on the shape so that the simple shape can get, you still get the same dimensional shape, but it's slightly more complicated possibly. And so here on the left, we have the boundary of a round ball, which we call the two-dimensional sphere. And we're doing surgery on the two-dimensional sphere, which means we take these two disks, we take them out, and then we glue in a cylinder whose boundary was the boundary of the two disks. So the surgery procedure allows us to go from a sphere to a donut. And so they're connected by surgery. And so this can be done in higher dimensions. So combining these two steps, you can create a lot of complicated high dimensional manifolds. You can sort of take products and so on, and then you can do surgery on the simplest things you get to then produce more complicated things in that dimension. Okay. All right. So let's now look at what are symplectic manifolds. And so this is an invitation to symplectic geometry. So the talk will not be super technical. I'll talk about the ideas from where these terms were born. And so symplectic geometry is something that was born out of physics. It was born out of the study of celestial mechanics. So physicists in the 16th and 17th century were interested in trying to predict the orbits of planets. We were trying to figure out like what light is and how it travels and so on. And a lot of the study they did actually motivates the study that we do now. And it's turned out that what they were doing is actually symplectic geometry and contact geometry. And so some objects in symplectic and contact geometry are these caustics and light. So the way shadows form, the way light interacts with shadows and the way these are formed, these actually give you interesting objects in symplectic geometry. Okay. But so let's look at a more formal definition. A symplectic manifold is a 2n-dimensional manifold with a closed non-degenerate 2-form omega. Now that's, if you have never taken differential geometry, that might make no sense. And so what is a way to think of, like, what does it mean to have all of this? So we've talked a bit about what, so we, at this point, we possibly have an idea of what the word manifold means. And we have an idea of what the word 2n-dimensional means, right? So it's the 2n-dimensional manifold is just some shape where there are like 2n directions, where n can be any number. So symplectic manifolds are necessarily even dimensional. They can be 2-dimensional, 4-dimensional, 6, 8, and so on. And so what is this closed non-degenerate 2-form doing? So what all these words mean is that you just have a way to measure sizes of 2-dimensional submanifolds. So that's not a very accurate thing, but mathematicians often rely on intuition to think of complicated definitions. Like when you do math, you have to be very precise, and so you have to like introduce a lot of adjectives. But as humans, we like to think of terms and of concepts in more intuitive ways. And so what this means is in symplectic manifolds, there's this consistent way of measuring two-dimensional submanifolds, like shapes inside this manifold that are two-dimensional. There's a consistent way to measure their sizes. So another way of trying to motivate this is we can think of like what is like this starts with talking of a 1-2 form, but if you have never seen forms before, then why start at 2? Maybe we should start at 1 forms. Or maybe we should start at 0 forms. A 0 form is a function. So that's all a form is a 0 form is just a function. Okay, so a non-vanishing 0 form would just be a non-vanishing function on a manifold. Okay? And a non-vanishing 1 form you can think of is a consistent choice of direction along the manifold. Now there are manifolds where you can't find a consistent choice of direction. You would have to go up to dimension 2 for that. And so this is an example of a non-vanishing 1 form. A non-vanishing 2 form is, if you try to sort of, go from that intuition into a 2 form, is it's a choice of like 2 directions at every point. And you can keep choosing 2 directions, and none of the directions will have to collapse. And so that's the idea behind the symplectic manifold. And this is like a very strange technical definition, and it doesn't give you a lot of intuition about what a symplectic manifold is. And that's part of the reason why all of this research is happening, is we want to understand. A lot of the research is really tries to understand, well, what does it mean to be symplectic? Okay, are there any questions?
There's a question in the chat.
Yeah.
They're asking, what are we choosing directions for? Anhad Jha is asking, what are we choosing directions for?
So we're not choosing the directions for anything. The idea is that you can choose directions. So the existence of a form will say that you can choose directions. And you can think of that, you can choose directions to sort of move in that space. Like if you can think about this, that if you've been in a security line at an airport or something, you can imagine that the only direction you can move in is the direction the line moves in, right? It's not, you can't move left to right, you have to move straight and so on. So when you have a topological shape, there's not a lot of direction you can move in. And sometimes it happens that you may not be able to find a consistent way to move off a shape. So you can try to do this on a sphere, for example. So this is a non-vanishing 1 form on a cylinder. I didn't draw the vertical direction, but you can imagine that if you're on a cylinder, you can sort of move up or move left or right. But imagine the surface of a round ball. If you try to draw arrows on the surface of the round ball, and if you want to do it in a consistent manner overall, you will find that at the poles, your arrow has to have like 0 length, just if you want to make a smooth or consistent choice everywhere. And so a two-dimensional sphere is an example of a manifold that doesn't have a non-vanishing one form. And so that's maybe think, so if that doesn't make sense, I'm just saying that on certain shapes, there are ways to move. And if you want to make sort of move on every point in a consistent way, you might not be able to do that. That makes some sense. So let's try to move forward and see if it's not making a lot of sense. Just think of symplectic manifold as being some even dimensional manifold with some sort of structure on it, which is a little where we care about whether we can actually move around on the shape in some way.
Yeah, he said he got it.
Okay, good. Thanks for the question. Yeah. Okay, so let's look at some examples of symplectic shapes. And so when we have a symplectic shape, so what a symplectic structure does is it gives you a way to measure the size of the overall shape. Okay, measure the volume of the overall shape. So if you're looking at two-dimensional things that have symplectic structures, then we can specify what the area of that shape is. So an example of a two-dimensional symplectic object is the boundary of the round ball, the two-dimensional sphere. And we just say here, this is a sphere of area 1. So this notation, omega subscript st, means standard. So everything we'll do in this lecture is just going to be about the standard symplectic structure on Euclidean spaces or their submanifolds. You can ask about, that's more in the vein of the classification problem we asked before. Can you have non-standard symplectic structures and so on? That's not something I'm going to talk about today. Okay. So this is an example, a symplectic sphere. R2, which is just the plane, has a symplectic structure, which we call the standard symplectic structure. And then you can also have symplectic structures on disks. And this is, you can think of just the disk, the flat disk sits inside the plane R2. And so the symplectic structure on R2 restricts to a symplectic structure on the disk. And this is a disk of area 1, this is a disk of area 2. So radius is sort of square root of 2, and there has to be a pi in the area that we sometimes suppress. So when we say d21, we might actually be meaning d2 of pi. So these are some choices we sometimes make. Okay, so these are some examples of symplectic shapes, and these are friendly shapes. These are things we are used to seeing, or we can visualize, and they have symplectic structures. Now, what we talked about before is when you have shapes and you want to get higher dimensional shapes, you can take products. And so if the disk is a symplectic object, well, we can take a product of two disks, and it turns out we can get a symplectic structure on the product. And now this is something 4-dimensional. These are both individually 2 dimensions. So dimensions get added when you take products. And so this now already is pretty hard to visualize, but we can talk about it. We can write down formulas for it, and we can study the shape, even though we cannot really think in 4 dimensions. So D2 cross D2 is an example of a 4-dimensional symplectic shape. Another example is B4. B4 is the four-dimensional ball. Now, one way to define the ball is it's the set. So if you think of what is three-dimensional ball, you can think of you have three-dimensional XYZ plane, and the ball is the set of all points that are distance at most 1 from the origin. And so similarly, the four-dimensional ball can be defined as, well, you have now a four-dimensional Euclidean plane. Suppose the coordinates are X, Y, Z, and Z, and W. The four-dimensional ball is the set of all points that are at most distance 1 from the origin in four-dimensional Euclid. And this is a shape that has a symplectic structure. Okay? Or we can say that if the coordinates are x1, y1, x2, y2, the ball is x1 squared plus y1 squared plus x2 squared plus y2 squared less than equal to 1. Another shape is the ellipsoid. So the ellipsoid can be defined as the set of all points that look like this: x1 squared plus y1 squared plus x2 squared plus y2 squared over 4 equals 1. Now this is a pretty complicated looking expression, but one way to think about these things is think about like lower dimensional analogs. Now, an ellipsoid looks sort of scary, maybe. There are 4 variables, but you studied ellipses. And so ellipses are just the corresponding ellipse for this would just be x squared plus y squared over 4 equals 1. And so somehow this just, you're taking a similar idea, but just doubling the dimension. Okay, so these are some 4-dimensional symplectic shapes you can study. And so something that's interesting is these shapes we just talked about. We had the 2-dimensional disk cross the 2-dimensional disk, or 2-dimensional disk cross the 2-dimensional disk, where they have different areas, or the 4-dimensional ball, or the ellipsoid. Now, it turns out that topologically, so if you forget the symplectic structure, we just look at them as topological manifolds or smooth manifolds, and we're allowed to do deformations that do not respect the symplectic structure. They are all the same manifold. They're all balls. And you can maybe think about that in a lower dimension is, if you think of the 2-dimensional analog of this, it's just the square. It's just the boundary of this thing I've just drawn. And so this is sort of the analog of a square. This thing is the analog of a rectangle. This is the analog of a circle, of a disk. And this is analogous to an ellipse. And you can think that you can deform all of these into the same shape. But what happens is when you do that deformation, you change the symplectic structure. So as symplectic objects, they are different. Okay. So you have these symplectic structures. And as I said, the definition of symplectic is sort of strange. Like, even if you have studied differential geometry for 10 years, like I have, I mean, and people have studied it for like their lifetimes even, it's still like we don't really have a good intuition for what it means to have a closed, non-degenerate 2-form omega. It's a really strange definition. And so, like, what does it mean to be symplectic? And what are ways to modify a manifold that preserve its symplectic structure? So these are called symplectomorphisms. And so these are questions that drive the research here forward. So it turns out then, where if your symplectic object is a 2-dimensional manifold, then any volume preserving smooth deformation is a symplectic deformation. So when you're in really low dimensions, so all the first examples of symplectic objects we saw, it turns out that as long as you're preserving the volume or the total area, you're doing symplectic deformation. If you think back to that old example we saw of a geometric embedding problem, where we asked when does one manifold fit into another, and we took the purple thing and we folded it while preserving its area. This was actually a symplectic embedding. So this symplectic rectangle actually fits inside the symplectic blue square as a symplectic embedding. And so in low dimension, symplectic just means volume preserving. So are there any questions at this point?
Yeah, there is another question from Orko Prabhodash. He's asking why we are only looking at symplectic manifolds having even dimensions. And there is another question from Anhad, who is asking if the choosing directions is anyhow related to orientability.
Oh, okay. So these are really good questions. So for the first one, it just turns out that if you want a symplectic manifold, if you want this closed non-degenerate 2 form, you have to have an even dimension. And there are odd dimensional manifolds that have a similar structures, and those are called contact manifolds. And so when people do research in symplectic geometry, they also study contact manifolds, which are the odd dimensional things as well. And for the next question, yes, that the choice of directions does determine an orientation. So when you choose a symplectic form, it does give you an orientation on the manifold. So these manifolds have to be orientable, and the choice of symplectic form gives you an orientation. So and yeah, if those are words that are new to any of the other listeners, then it's you don't have to worry too much about those. Okay. All right. So let's just. Did that answer the question? How do you feel about this?
Yeah, they're saying yes.
Okay, great. Thanks for the questions. Okay, so let's reset. We're looking at symplectic embeddings now, and we see that when we're looking at two-dimensional symplectic embeddings, they just have to be volume-preserving embeddings. So if we sort of squeeze the purple thing in the middle and then fold it, as long as we don't change the area, everything we do is a symplectomorphism. Everything we do preserves the symplectic structure. So these are symplectic embeddings. And so around the 1970s, people had defined symplectic structures, and they weren't really sure if symplectic was equal to volume preserving. So they were like, well, we have this complicated definition, but is it just another way of describing volume preserving things? But it turns out it's not. So this was the result that really, said that symplectic geometry is something really deep and interesting. And so in 1985, Gromov proved his non-squeezing theorem. So what he proved was you take the 4-dimensional ball that has area, that has volume equals 2, with the standard symplectic structure. There's no way to symplectically embed it into the product of the disk of the 2-dimensional disk of area 1 cross R2. So this is something that has finite area inside something that has infinite area, but you can't sort of embed it in there. And so a schematic in half dimension is something like this. The half dimensional analog of this is the disk with area 2, and the half dimensional analog of this is sort of this vertical strip inside R2. And so what Gromov showed is that you can't, while preserving symplectic structures, you can't take this round object and sort of squeeze it in this vertical space. So you can't sort of squeeze it in. If you, I mean, we know we can do this in for the dimensions this picture is drawn, because in dimension 2, a symplectic embedding is just a volume preserving embedding. So you can just squeeze it and put it in. But once you go to dimension 4, you can't sort of squeeze two directions while preserving the symplectic structure. So that's what Gromov proved. And this was really strange because it's intuitively, we don't really understand why this doesn't happen. I mean, we have a mathematical proof, but it's still really interesting. And so this is why we have the symplectic camel. As you can imagine, that if this camel was a smooth camel, then it could just squeeze its head small and get itself out of the ring it's stuck in. But if it's a symplectic camel, it can't squeeze its head into something small, so it's stuck. So this is a famous cartoon that came out after this result was proved. And so this meant that symplectic geometry and symplectic embeddings capture something intrinsic, something sort of super interesting. And so this is the statement of the theorem. So when you have an arrow with the superscript S, that means a symplectic embedding. And so the theorem that Gromov had proved was, if you want to embed the ball in 2n dimensions that has volume R inside a two-dimensional disk across 2n minus 2 dimensions of Euclidean plane, the area of the disk has to be bigger than the area or the radius of the ball. Does this statement make sense? Are there any questions?
Can you just go over what you said about half dimension schematics in half dimension?
Yes. So yeah. So I wanted to convey like what this statement is saying, but I can't draw four-dimensional things. So instead of drawing four-dimensional things, I drew two-dimensional things. So everything that's four-dimensional in the statement here is two-dimensional in this picture. And so a schematic is like a cartoon. It's like, in reality, this symplectic embedding exists as it's drawn, but if you think of it as a schematic, then this embedding does not exist, is what I meant.
Okay, thanks.
Sure. Right. So this was the non-squeezing theorem. So that meant, so this was the first interesting example of an obstruction to a symplectic embedding. And the obstruction came from some sort of studying certain algebraic geometric objects. And it used, functional analysis, complex analysis, topology. So symplectic geometry is the intersection of a lot of different fields of mathematics, and it really started with this paper of Gromov. And so the punchline of what Gromov did was that, well, symplectic is not just volume preserving, because we just saw the non-squeezing theorem says you can have something that is finite volume, but you can't symplectically embed it in something that is infinite volume. So that led to a lot of interesting questions being asked. And so the standard embedding question, just in dimension 4, was, well, when does this product of disks embed inside a ball? So if we don't allow infinite dimensions, if we restrict to finite dimensions on our shape and our target, what sort of restrictions do we have to place on the parameters to ensure there is an embedding? So, we can ask this for products of disks inside balls. We can ask this for ellipsoids inside balls. And we can also, this is an analog of a packing problem. So a lot of research in geometry is about, when does a configuration of spheres, what is the optimal packing of a collection of balls inside a larger ball, and so on. So this is a symplectic analog of that. How many balls can we pack inside a bigger ball, and so on. So these are the symplectic embedding questions these are still being studied in some ways. And so I wanted to give a quick idea of how do we actually visualize four-dimensional manifolds. So the idea here is that, so as I said before, I had to use a half-dimensional schematic there. Right? There's no way for us to actually see four-dimensional objects. Right? We live in a three-dimensional space, and even visualizing three-dimensional objects is hard for us. So there's no hope for getting four dimensions. The way to do that in some simple cases is through what's called toric geometry. And a toric geometry is something that's much more a part of algebraic geometry. But as I said, symplectic geometry is the melting pot of a lot of different kinds of mathematics. So it borrows techniques from wherever it can. So algebraic geometers have given us toric geometry. And so the idea of toric geometry is sort of simple. You take any point in two-dimensional complex plane,
Sorry to
which is...
interrupt. Someone has a question on the chat.
Yes.
Arko Prabhu is asking, how do we know that at least for 2 dimensions, a symplectic embedding is same as a volume-preserving embedding?
So it's from the definition that the volume in 2 dimensions is measured by a 2 form, and a symplectic form is a 2 form. So that is the idea. And then so if you're preserving the 2 form, you're doing something more symplectic, and you're doing something volume preserving. In higher dimensions, the volume, so if you're in a 4-dimensional manifold, the volume is a 4 form. And if you don't know what forms are, the volume is something that depends on the data of the symplectic form, but it's not all the data of the symplectic form. And so if you're just preserving that little bit of data in higher dimensions, you're not preserving everything about the symplectic form. But in 2 dimensions, the data of the volume and the data of the symplectic form are one and the same. So that's why volume preserving is symplectic in 2 dimensions. Does that make sense? Okay. So I'm going to just talk about toric pictures now. And so the idea behind toric pictures is that you take a point in 4-dimensional space or 2-dimensional complex space, and you map it to R2, which is a 2-dimensional space, via just taking the squares of their moduli. So this is the map. And so like what does it do for us? Well, it allows us to visualize certain shapes. So if you think of a ball, a 4-dimensional ball of radius 1, then that's described by z1 squared, the modulus of z1 squared plus the modulus of z2 squared less than or equal to 1. So the image is just going to be a triangle. This triangle is just the area in the first quadrant underneath x plus y equals 1. And so a ball is just going to be represented by an isosceles triangle, isosceles right-handed triangle. A product of disks is going to be represented by rectangles, and these are called polydisks. I'll just leave these images up for a bit. And then an ellipsoid is going to be represented by scalene right-handed triangles. Okay. And the shape that came up in the non-squeezing theorem is sort of this vertical strip. So the schematic that we drew was actually not too bad. And that this also often happens in math, is that you make a guess for, this is the only way I can do something. And it turns out that guess might have some mathematical interpretation. Okay. So this is some way to visualize these shapes that are 4-dimensional in pictures that we can actually see and understand. Okay. So these are toric pictures of these shapes. And so we can now visualize simple embeddings So if we want to visualize an ellipsoid into a ball, well, we just need to draw a big ball and the picture of an isosceles right-handed triangle and a smaller scalene triangle that fits inside it. And as long as it fits inside, we have visualized an embedding. And a polydisk into a ball is exactly something like this. So polydisk is represented by rectangles. So when we have a rectangle inside a ball, we've managed to embed that polydisk into a ball. So toric geometry allows us to visualize these embeddings. But it also allows us to build embeddings that we a priori might not expect to exist. So we can ask something like this, where, if you have the ellipsoid E41, which is represented by a scalene triangle of, one side length 4, one side length 1, and we have the ball, which is of like slightly bigger than 2. So this triangle, these pictures don't fit inside the other. The blue scalene triangle, the picture we draw for the toric picture does not fit inside the gray. So it seems like there's no way an embedding can happen, but there is no volume obstruction. The volume of this is 4. The volume of this is just bigger than 4. So we can ask, well, the volume obstruction seems to vanish. And it also turns out that other algebraic obstructions, like the ones Gromov used, they also don't seem to exist. So we can ask, well, is there actually an embedding? And the same thing happens for this polydisk inside this ball. And so remember, polydisks are represented by rectangles, and balls are represented by isosceles triangles. And then if you draw the rectangle and the ball, it turns out that the rectangle just sticks out of the ball. It's not quite an embedding. And so but again, the obstructions seem to vanish, and we don't really know if an embedding exists. Well, a priori, we don't know. We have results. So it turns out that there are tricks you can do with these pictures such that you modify the pictures to represent the same manifold, but you introduce some sort of singularities or some sort of, interesting stuff. And there's a lot of math that goes behind them, but the end result is really satisfying. So we can see the end result and try to appreciate it. But if you are interested in learning how this happens, you might have to do a deep dive and actually learn what symplectic geometry is. But it turns out that you can take the gray isosceles triangle for the ball and have a scalene triangle representing the ball by a process called mutation. But you introduce some sort of singularity, but it's not a singularity of the ball. So, and then you can sort of fit the blue scalene triangle inside that gray shape, and that's a way to. So that's an ingenious construction to produce these embeddings. And another way to produce these embeddings is by a procedure called folding. So remember the thing we did with that purple rectangle inside the blue square is we folded the rectangle and we were able to fit it inside the blue square. And so something that Felix Schlenk came up with in sort of late 1990s is a sort of similar procedure, but for 4-dimensional objects. You can take these 4-dimensional objects and very intricately define something that looks like folding in the toric picture, and it allows you to embed things. And so by doing these sort of tricks, you can find embeddings that don't a priori seem to exist. So let's move on. So this is like what was promised in the title is there was some infinite staircases and Fibonacci numbers were promised. So this is where the infinite staircase comes up. So McDuff and Schlenk were exploring the embedding problem in full generality. They were asking, when does an ellipsoid fit inside a ball? Okay, and so A is a parameter for the ellipsoid and mu is the parameter for the ball. And they came up with this graph that was able to say exactly when it fits. And this graph has like a really intricate and beautiful structure. So what happens in this graph is, so we're plotting with the line that has these the sort of staircase looking line is the plot of this graph. It sees which is the smallest ball an ellipsoid fits in. The blue line is the volume obstruction. Now, if an ellipsoid fits inside the ball has to have a sufficient amount of volume. And so the blue line says, well, it has, that's what the blue line detects. What they found was the embedding function sort of is a combination of straight lines that all hit the origin and horizontal pieces that go all the way to the volume obstruction. So at these red dots, you have embeddings that exactly meet the volume obstruction. So that's the optimal embedding. Inside these two dots, you have points that you know you have to be much smaller than the volume obstruction. And it turns out that the points where you can have an embedding that's equal to the volume obstructions are ratios of odd Fibonacci numbers. So assume you're familiar with the Fibonacci sequence, where where every number is the sum of the previous two numbers of the sequence. And it just turns out that the Fibonacci numbers show up in this very geometric problem. And you have an infinite staircase near tau to the fourth, where tau is the golden ratio, which is the ratio of the limit of Fibonacci numbers. And so as you approach tau to the fourth, you have infinitely many points where you hit the volume obstruction. And so they discovered this incredibly intricate structure. And since then, it has shown up for other embedding functions of ellipsoids. So this is a recent paper from like 2020, by 4 authors. And so these are ellipsoid embedding functions for other manifolds, which are not necessarily the balls. And in many cases, these infinite staircases keep showing up. And so a question you might ask, well, why Fibonacci numbers? Why do these numbers show up in a question that's like purely geometric in some sense? And it's not just Fibonacci numbers. Like several interesting classes of numbers show up mysteriously in symplectic geometry. You have Fibonacci numbers. There are things called Markov numbers, which are a generalization of the Fibonacci numbers. There are things called Pell numbers, which are also recursively defined like the Fibonacci numbers in some sense. And a lot of research goes into understanding, well, why does this happen? Like once you find the ellipsoid embedding functions, well, you solve the embedding problem, but then you're curious as to why does this pattern show up? And it turns out that symplectic geometry, a lot of these things can be explained, or might be explained by connections to other fields that are called, well, there's a field called mirror symmetry that's born out of physics. There's something called cluster algebras, which is studied by representation theorists. And then there are connections to physics that might explain some of these numbers. And these are all areas of active research. And so, yeah, I'll stop there. Thank you for your attention.
Does anyone else have any questions?
Hello, am I
Hello.
audible? Yeah.
Yes.
Yeah. I want to study differential geometry as well as algebraic topology in the future. So if I enroll in a differential geometry course, will I need to study algebraic topology separately as another course, or will I be introduced to it in the differential geometry course only? Or that
No,
depends on the course in which I am enrolled?
they will typically be separate courses.
Okay.
There's some overlap, but in the differential geometry course, you will learn more about differential geometry and forms and so on, not so much about algebraic topology.
Okay, sir. And another question, sir, can you state some applications of these Fibonacci numbers or Markov or Pell numbers in physics?
No,
Especially,
I'm not super aware of applications. In some sense, these show up, but yeah, I don't think I could give a very simple explanation or answer to that question. But you can try to find out. There's not an easy explainable answer, I think.
okay. Means I was asking if these concepts are used in celestial mechanics especially or in some other branches.
So they started in the study of celestial mechanics, but right now there are applications to, like, there are more connections to string theory now that I myself don't understand super well, so I couldn't help you too much.
Okay, sir. Thank you.
Okay. Thank you for such a wonderful talk. Now I'll end the meeting, and everyone, please join us tomorrow for the participants. Please join tomorrow for our talk. Thank you.
Okay. All right. Thank you. Thank you
Bye.
all. Have a good evening. Please enjoy the rest of the camp.